Morning, grade nines. And so this is looking at outcome number 3, part 4. So in order to figure out how far objects are in space, we can use a method called triangulation. And basically what you're doing is you're doing a scale diagram and doing the measurement. Because there's some stars that are, thousands of light years away. And with today's technology, we're not going to be getting there anytime soon. But we've been able to figure out how far away they are using triangulation. And so here's the notes. Let's go through these, and then I'll show you how to do it. Triangulation is the method of measuring distance indirectly by creating an imaginary triangle between an observer and an object whose distance is to be estimated. With triangulation, the longer the baseline, the more accurate the results. And so here we have our triangle. Okay, and there's your baseline. So you need a baseline and you need two angles in order to make your scale drawing. Okay, so like there's a tree there. These people want to figure out whether they have the ability to swim all the way to the tree, but they're having a hard time figuring out how far away it is. So what they do is they create a baseline here that you can walk that out. Like maybe how many steps this is. They measure two angles. You've got your own built-in protractor right here to try and do that. Measure your two angles, and then in the sand they will draw a scale diagram of it, right? And for their scale diagram, 1 centimeter is 20 meters, and so they make their two angles and they draw their triangle, and there's the tree, and they measure this, and it's 8.2 centimeters. And every 1 centimeter is 20 meters, so they multiply that by 20 to find out that it is 164 meters away, and they can swim that. There's also a formula for percentage error that I want you to learn to use this year, because you're going to be using it next year in science quite a bit. Percentage error is equal to actual minus estimate, absolute value of it, so it doesn't matter whether it's plus or minus, divided by what's supposed to be, times 100%. All right. Now let's go ahead and see how this works in real life. So I have a blank screen here. I'm going to move this. Whoops, I actually have a triangle already done. Okay, and so let's go ahead and erase some of this. Erase that part. And then I have my two angles. I'm just going to write them down on the side here. That's down on the side here. 75 degrees and 78 degrees. Okay, and then we'll erase this part here. Erase this as well. All right, so let's say we see an object out in the distance, and it's we want to figure out how far away it is. So we want to draw a triangle. Okay, and so we walk out a baseline at the bottom, and we see that it's 46 meters long. Well, I need to draw a triangle that's smaller than that. So I'm going to go ahead and draw this. So I'll use the scale. 46 meters is 4.6 centimeters. So I'm going to grab this. And always draw your triangle starting at the bottom of a page, because you don't know how tall it's going to be. Let's go ahead and draw this to be 46. Yeah, 46. And then from each end of that baseline that I've set up, I use my protractor and I measure the angle to my object. Okay, and so the numbers were 75 and 78. And then I need to put that in my picture. So what I do is I take my protractor, I'm going to put it on, and it works half on, half off. And the first angle is 75, so 0, 4, 50, 60, 70, 75 is right there. Well, what does that mean? It means somewhere along that edge, going up, is my object. I don't know how far it is. I'll just make my line as such. The other angle is 78 degrees. So I'm going to go to the other side. I'm going to hang my protractor half on, half off, and go 0, 0 all the way up to 78 and put my dot there. I'm going to grab my ruler and extend that line up, and where the two lines meet, that's where my object is. Okay, there's my object. Now I want to find out how far away it is. I take my ruler and I just measure the distance right down the center. 80.5. Sorry, 8.5. So right down the middle, that's 8.5 centimeters. So 8.5 centimeters means in real life, my object is 85 meters away. Okay, not bad. I think my estimate was 90. So if I want to go ahead and do my percentage error calculation now, so it's 90. Okay, and then so here, that has to be given. 90 centimeters actual, in case you're wondering where I got that number from. Okay, so 90, take away 85, absolute value, divided by 90 times 100%, and that's 5 divided by 90 times 100. 5 divided by 90 times 100 gives me 5.6% error. Okay, so you can see, you have your baseline, you have your two angles. That one was 75, that one was 78. You did your triangle, measured down the center to get how far it is. I mean, that's the principal thing we're trying to do. And then percentage error, just something you're going to need for next year. So I figured I would show it to you now so you'd be better prepared. Okay, and then there's assignments for you to do. Okay, by the way, your brain does this automatically. It looks at objects from two different viewpoints, your both eyes. It actually does a mental calculation of the angle, and it knows its baseline, and it gives you an estimate of how far away an object is. Okay, and so, but for going to do stuff in outer space, we need to be a little bit more accurate than just your eyes looking at the stars and trying to figure out the distance. And the largest possible baseline available to us here on Earth is actually, you don't even have to leave Strathmore to do this. You just take your reading. Take your reading, say in January, wait 6 months. And so what's going to happen is 6 months later, so you take your reading here, and then 6 months later, the Earth is on the other side, and you take another reading. That gives you the largest possible baseline available to us here on Earth is the diameter of Earth's orbit around the sun. Why does this work? It works because of parallax. So, I'm reading. In order to work from the largest possible baseline possible without leaving Earth, two sightings of the same star taken 6 months apart, and therefore the baseline is the diameter of Earth's orbit. Here you can see, right? Take a measurement here in January, here in June, whatever, 6 months apart, or whatever star it is, and then you could do that. And parallax is the apparent shift in position from two viewpoints. You have your background of stars, so your frame of reference, so that you would know that you're looking at the right thing. And you can see parallax, by the way, if you look at something, cover up one eye, and then look at the same object with the other eye, and you'll see the apparent shift in position. Okay. To measure these distances within our solar system, we measure something called AU, astronomical unit. And an astronomical unit is defined as the distance from the Earth to the Sun. Right? That's a person-made object. It's about 150 million kilometers. Okay. Now, if you want to go outside of our solar system, so you got to use the unit light year. Light year is the unit how far light travels in 1 year. It's 63,240 astronomical units, or if you want, it's 9.5 trillion kilometers. So if there's something that's 2 light years away, you take 9.5 trillion and multiply by 2. If it's 10 light years away, 9.5 trillion kilometers times 10, which means it's 95 trillion kilometers away. And light travels at the speed of light. So if I shine a beam of light out the window and I wait 2 years, it goes 2 times this, 19 trillion kilometers in a couple of years. I think we're live on triangulation. And then we can look at the solar system up close. Okay, so the sun, right, mostly hydrogen gas, 1.4 million kilometers in diameter. It's 110 times bigger than Earth. It's so hot that the gases glow. The sun is not on fire. That's a nuclear reaction that's going on. At the core, 15 million degrees Celsius. That's hot enough for a fusion reaction. I think you need to make a fix in your notes where hydrogen fuses together and changes into helium. And the surface is constantly churning. Some areas are hotter, some are colder. The cooler areas are called sunspots. They're these little black, they look like black spots on the sun. And right around them, there's like volcanic eruptions, but it's eruptions of solar flares. And that material goes off into space. When it comes towards Earth, it does get pulled into the north or south poles, and we get the northern lights or the southern lights. Okay, and that stream of high energy subatomic particles going to space, those are called solar winds. Okay, and traveling through our solar system in 1969, July 17th, Neil Armstrong and Aldrin landed on the moon. And we have satellites that we send into space to further explore the planets as well. We have rovers on Mars. See, that's pretty. We have more than one rover on Mars, and we are eventually going to be colonizing Mars. So a lot of progress is made since the textbook was published. Planets, it's important to know, they're all different from each other. They're different in size, motion, composition, density, temperature. The inner planets are the first 4. Okay, and so you by now know the first 4: Mercury, Venus, Earth, Mars. Okay, those are the first ones. They're all terrestrial. They're all rocky, so you can land on these and go and explore. The outer planets, the last 4, we don't include Pluto anymore. It's a dwarf planet. It's still there. Nothing's changed, but we don't count it as a planet. Those are gas planets. Okay, the inner planets tend to have less moons. Okay, probably if they were going to make a moon, that material got pulled into the sun. The outer planets tend to have more moons. Okay, and of course, the hottest planet is the second one in, right? Because it has a big atmosphere. Mercury, even though it's close to the sun, doesn't have almost has no atmosphere whatsoever, and therefore it doesn't really get hot. Atmosphere helps trap it. Venus has mostly carbon, 96% carbon dioxide, so it's like a global warming planet of all of them. And of course, the years are shorter with the planets that are closer to the sun. Okay, and the years are longer for the planets that are outer because it takes them longer to go about. Okay, and then place these in order from smallest to largest, and there is a list. Smallest is meteorite, then meteor, then asteroid or comet, then moons, dwarf planet, planets, the sun, nebulas where stars are born, the galaxy where there's lots of solar systems, and the universe. You should have a rough idea from largest to smallest, the sizes of those. And then there's some information on the planets. we did this information is all in the books. You have to do a quick little worksheet on it that you will check out. It's in your notes. Here, I mean, here's the information given to you. And then looking at the outer planets, okay, we've sent 2 spaceships, Voyager 1, Voyager 2, out into deep space. They are now actually outside of our solar system, in between our solar system and the next one. It's called interstitial space. They had all kinds of sensors. They're traveling at 16 kilometers per hour, which is really fast for here on Earth, but in space, kind of slow. And so far, they've gone past Jupiter, Saturn, Uranus, Neptune, Pluto, and taken pictures and sent them back. But once again, they're really far away, so they send digital pictures. And those digital pictures with the lag takes about, now it's 2021, it'd probably take about 44 hours for those pictures to come back to us. So there you go. You send a message, turn on, take picture, click. That takes about 24 hours to get there, and then it sends it back. It takes another 22 hours to get back. Okay, and that is the end of outcome number 1. There's the assignment that you would do, and there would be a quiz coming up soon as well.